In this talk we will be dealing with interfaces, which in the context of battery modeling would very likely mean electrodes in contact with some kind of solvent that contains electrolyte ions. For example, a graphite electrode surrounded by molecules of ethylene carbonate in which there's an occasional lithium cation and a hexafluorophosphate anion. Atomistic systems like these can be described near exactly with so-called first principles methods. When I say first principles, I mean that these kinds of calculations do not rely on any experimental input. We can derive the behavior of the electrons in the system directly from the principles of quantum mechanics, that is, by solving the Schrödinger equation. I'm talking about electrons here because it's almost exclusively the valence electrons that dictate the chemistry of what is happening. The nuclei, so protons and neutrons, can be described classically to a very good approximation. Thus, the wave function in a Schrödinger equation depends on the electronic degrees of freedom. It's a function of as many position variables as we have electrons in our system. Unfortunately, we know how to solve the Schrödinger equation exactly only for one electron, and as soon as there are more, it becomes a numerical nightmare. Mostly because the wave function depends on so many independent variables. So in practice, we would be using what is known as density functional theory, an ingenious technique that recasts the problem in terms of the electronic density, a quantity that is local in space, meaning it only depends on one coordinate. The main problem with density functional theory is that it scales cubically with the system size. That basically means that if you make your system 10 times as big, the cost of your calculation increases by 1,000-fold. This means that conventional density functional theory can do at most maybe 1,000 atoms. The toy model of the interface that I showed on the previous slide had 3,500 atoms already, so it would be out of reach. Fortunately, over the last 2 decades, clever people developed a more involved flavor of DFT called linear scaling DFT. As the name implies, here the effort scales linearly with the system size. In our research we use an approach called ONETEP. It can easily deal with tens of thousands of atoms, as you can see in this plot. ONETEP has been described in a separate talk by Chris Skylaris. But even with ONETEP, many interfaces of interest would be out of reach if we tried to tackle them directly. The main issue here is the solvent and the electrolyte, which can easily contain hundreds of thousands of atoms. And, moreover, we need to study large numbers, at least hundreds, of configurations of the solvent and electrolyte molecules to properly sample its behavior. This is what physicists call averaging out solvent degrees of freedom. So, to make this feasible, we will only retain the quantum description of the electrode, but the solvent and electrolyte we will model with a simplified continuum approach. We use a technique that is known as implicit solvation. We replace the solvent with an unstructured dielectric continuum, something that has no internal structure but can polarize in response to our quantum system, which is known as the solute in this context. Being able to polarize is the most important feature of a solvent, and this model covers that. The solvent is placed outside of a cavity which holds the solute. This cavity needs to be suitably constructed, but this is not important here. To figure out the behavior of this implicit solvent, we need to solve the Poisson equation, and this is handled by a piece of software known as a multi-grid solver. This simple example I'm showing you here uses open boundary conditions. It's an isolated molecule, but for the study of interfaces we would be using so-called periodic boundary conditions. So a situation where the system is artificially replicated in all or some of the directions. This is what is represented here, perhaps poorly, by the white dots. You have to imagine that the system extends periodically to the left and right and into and out of the screen. This is done mostly to avoid surface effects. We want to study how the solvent and electrolyte interact with the surface of the electrode and not with the edges. One important feature of periodic boundary conditions is that they require the system to be charge neutral. As you will see in a moment, this will be very important. Now, I explained how we model the solvent in a continuum fashion, but what about the electrolyte? Well, we also treat it in a similar way. We model it by a charge distribution or a concentration distribution of so-called Boltzmann ions. These are point-like ions that affect the electrostatic potential of the system. The inclusion of Boltzmann ions makes the equation much more complicated. It becomes the Poisson-Boltzmann equation that you can see here on the right. But this is mostly the problem of the multi-grid solver. One thing that we need to take care of is to exclude the electrolyte ions from the immediate vicinity of the solute, so the electrode in our case. We normally keep them away at a slightly larger distance than we keep the solvent away. This is handled by a so-called accessibility function, which dictates where the electrolyte ions can go. You can see it as a sort of orange boundary in the picture. We now come to the question of charge balance. Let's assume our system is charged, because in principle this is what can happen. I'm using a potassium cation in this simple example. What are the electrolyte ions going to do? The oppositely charged ions will accumulate near the system, and some of the like charged ions will move away, escaping to infinity. You can see this in the concentration profiles in the plot on the left. That means that there is no guarantee of charge neutrality. In my example, in vacuum, the system would have a charge of +1, and in the electrolyte, the screening causes the charge to drop to less than +0.5, but still not to 0. This is because the box is finite. But it's actually periodic boundary conditions that we are interested in. We are modeling the extended, that is, periodic, interfaces. It turns out that in periodic boundary conditions, the total charge of the system must be 0, or else the electrostatic potential of the system diverges to infinity, and the energy per cell is also infinite. This is a well-known problem in DFT. It is normally worked around by adding what is known as a uniform neutralizing background charge, or historically as gallium. So, for instance, if I have a lithium cation deposited on graphene in vacuum, like in the picture on the left, I would be adding a negative charge density, that is 1 extra electron per volume, to neutralize this charge. So, while in the original charge density integrated to +1, the galliumized or shifted charge density integrates to 0. You can see the rigid shift in the plot on the right. The problem with gallium is that it is totally not what happens in electrolyte. In electrolyte, you would have the oppositely charged ions screening your charge system and neutralizing it locally. So the reality is different. Gallium is not a good model of reality because it acts globally through a uniform shift, and this would lead to artifacts. The problem with the kind of neutralization that does happen in reality is that, again, there is no guarantee of strict charge neutrality in a finite size box, so it's not suitable for periodic boundary conditions. So what do? We came up with a technique where the electrolyte concentrations are shifted a little bit in such a way as to ensure the total charge of the system is exactly 0. This tries to mimic the charge transfers that happen in open boundary conditions. Mathematically, this is what we do. We shift the average concentrations of both kinds of ions a little away from the asymptotic concentrations in an open system. The shift depends on the parameters of the electrolyte and the quantum system, as you can see. There are parameters to this shift, which we called xi, which need to be determined from the neutralization constraint that you see at the bottom. There's a slight problem in that there's an infinite number of ways in which you can come up with this shift and still get neutrality. So which of these shifts is the right one? Here we use a clever approach. There is a certain relationship between concentrations that holds in open boundary conditions. We use this in periodic boundary conditions to get a situation that mimics the open system as closely as possible. The final formula for xi is quite complicated, so I'm not showing it here, but trust me, it can be done. We can judge how well we are doing by comparing the concentrations on the faces of our cells against the known good asymptotic values from the open system. You can see this figure of merit in the plot on the right for 3 different electrolytes. The lower we get in the plot, the more closely we reproduce their reality. Crosses show the correct values picked by our algorithm. You can see that they are almost spot on. In the last plot, I am showing you an example prediction of our model compared against gallium. The system is a cation adsorbed on a graphene surface. We are showing the charge density of the electrolyte. You can see that with gallium you get artifacts, particularly at the bottom and top of the picture. With our neutralization by electrolyte concentration shift, we remove these artifacts and we also predict a larger concentration of oppositely charged ions close to the point of contact between the cation and the graphene. So, all in all, we have developed a hybrid model that is both affordable and accurate. Our model also works in periodic boundary conditions, where it is important to maintain charge neutrality. We know that gallium is not a good way to do it in electrolyte, and we developed an elegant, clever and accurate way of doing it right.